From my seat in the void, you and I are going to peer into the heart of our galaxy, Sagittarius A. It is 4 million times the mass of our Sun, 26,000 light-years away, hidden behind an impenetrable wall of dust. This dust has kept it secret for all of history. For decades, I have seen data of stars whipping around it at impossible speeds. Then the James Webb Telescope turned its infrared eyes toward the center, and what it found defies every mission prediction we had. Stars are igniting where nothing should survive, and water molecules exist in conditions that should vaporize them instantly. Mysterious gas glows with no clear power source. Evidence of black holes within black holes could rewrite how these monsters grow. By the end of this watch, you and I will understand why these are the most important black hole discoveries in decades. They are forcing us to rewrite the manuals on how galaxies evolve, how stars form, and what happens in the universe's extremes. Before I fire the thrusters, if you love exploring the depths as much as I do, take a second to like or subscribe. It is a simple gesture, but it helps this mission reach more curious minds. Now, let us begin our approach. Sagittarius A sits at the dead center of our galaxy. It is the anchor for every star I see drifting in the dark. That includes our home Sun, which circles this dark heart once every 225 million years. I have known about Sagittarius A for decades. We found it by tracking stars near the center and watching them whip around nothing. The mission started in the 1990s, when teams at the Keck Observatory in Hawaii began monitoring individual stars in the core. They gave these stars simple call signs like S1, S2, and S3. S stands for source, numbered as they were spotted. One star named S2 became a legend out here. S2 completes an orbit every 16 years, hitting incredible speeds. It hits 5% the speed of light at its closest pass. That is over 9 million meters per second. The gravitational forces are so immense that time actually runs slower for S2 as it brushes against the black hole. Light from the star is redshifted by the intense gravity. On the ground, they have measured this, and it matches Einstein perfectly. By tracking dozens of stars for decades, the crew determined the black hole's mass is exactly 4 million times our Sun. In 2022, the Event Horizon Telescope beamed back the first image, showing a glowing ring of superheated gas. The image showed a dark void, the shadow of the hole encircled by a brilliant, burning ring of gas. That ring is the inner edge of the accretion disk, the swirling graveyard of material orbiting the abyss. Friction and compression heat this gas to millions of degrees, causing it to pulse with intense radiation. The dark circle in the center is not the hole itself, but the event horizon, the ultimate point of no return. It was a triumph for humanity and proof Einstein was right. Once you cross that horizon, there is no escape. Not even light can break free. But here is the part that surprised me. The telescope only saw the hole itself. It saw the immediate zone around the event horizon, but could not see the wider chaos hidden behind the cosmic dust. 26,000 light-years of grit sits between my viewport and the center, made of remnants from dying stars. My eyes cannot see through it. Radio waves can, which is how the team finally imaged the black hole shadow. But radio data is blurry. Infrared light, though, passes through that dust almost like it is not even there. And that is where the James Webb Telescope comes in. It is the most powerful infrared eye we have ever launched. It launched in December 2021 and reached full power in mid-2022 after a long mission setup. The Webb mirror is 21.3 feet across, which is nearly 3 times the size of the Hubble mirror. A bigger mirror drinks in more light. Webb is built to scan the universe deep into the infrared heat spectrum. This heat vision allows us to peer through the dust that has veiled the galactic center since humans first looked up. For the first time, I can look through the cosmic veil and see the true chaos around Sagittarius A. What Webb saw shocked us all. Let's start with the impossible discovery young stars are forming right next to the monster. These stars sit in a region where physics says star formation should be completely impossible. Stars need cold, dense clouds to form. When a gas cloud collapses under its own weight, it shatters into clumps. Those clumps keep crushing down until their cores ignite with nuclear fusion. That is how a sun is born. It starts with molecular clouds, vast stretches of hydrogen and helium gas, laced with trace elements and dust. These clouds can span hundreds of light years and hold enough fuel for millions of stars, staying stable for eons. Internal pressure fights the inward pull of gravity, keeping it balanced. For a collapse to begin, something has to shake it. Maybe a nearby supernova explodes, sending a shockwave through the cloud. Or maybe two massive clouds collide, increasing the density. Or maybe the gas cloud gets so heavy that gravity just crushes the internal pressure. Once that collapse starts, the whole thing shatters. The thickest parts of the cloud cave in first, forming these isolated knots. As they shrink further, they start to cook from the inside out. All that falling energy turns into raw heat. Eventually, the heart of that clump gets so hot that nuclear fusion finally kicks in, usually around 10 million degrees Fahrenheit. At that heat, hydrogen atoms slam together, overcoming their natural pushback to create helium. That spark of energy means a new star is born. The fusion blast pushes outward, fighting gravity to a standstill. That balance keeps the star stable for the better part of its long life. It burns hydrogen into helium deep inside. But out here, near a black hole, things are different. It is an absolute radiation hellscape, gas screaming towards Sagittarius. A star forms a glowing accretion disk. It is spinning at nearly light speed, creating massive friction as the swirling material grinds together. That friction cooks the gas to millions of degrees. The gas glows with a blinding light, blasting out everything from radio waves to X-rays. This disk is a furnace of ultraviolet and X-ray radiation. Any gas clouds nearby should be scorched and ionized, making it impossible for them to collapse. High-energy photons just pummel the clouds with raw energy. They strip the electrons right off the atoms. We call that ionizing them. And let me tell you, ionized gas is incredibly hot. Those free particles are moving fast, bouncing around with insane energy. That pressure creates a wall that gravity simply cannot push past to form stars. Basically, the radiation from that disk should keep any nearby clouds too hot and agitated to ever collapse into new stars. Beyond the heat, the black hole tidal forces should tear any gas clouds to shreds before they ever get a chance to settle. It happens because gravity drops off with distance. One side of the cloud gets pulled way harder than the other, creating a violent cosmic tug of war. That stretch just rips the cloud apart. Near a supermassive black hole like this, those tidal forces are absolutely terrifying. For Sagittarius A star, those forces can destroy a gas cloud even if it is a full light year away from the event horizon. Anything inside that radius gets stretched and torn apart before it can ever hope to collapse. For years, we believed that making stars near a supermassive black hole was flat out impossible. This place should be a cosmic graveyard where nothing new grows. But the Webb telescope just spotted hundreds of young stars in that exact spot. These are not old drifters from across the galaxy. They are young, massive, scorching stars born within the last few million years. Some are practically infants. In space-time, they are newborns. They were born right as our ancestors back on Earth were first starting to walk upright on the African plains. In the grand scheme of things, that was yesterday. These stars are so fresh, they are still wrapped in their original blankets of space dust. When a star is born, not all the gas gets sucked in. A lot of it stays behind, swirling in a disk around the core. That is a protoplanetary disk. It might eventually become planets and moons, or the star radiation might just blow it all away into the void. Seeing those disks around stars near Sagittarius A star proves they were born right here. They did not just drift in from some quieter neighborhood. If they had started far away and drifted in, those fragile disks would have been ripped off their backs a long time ago. Other stars, or the black hole radiation, would have stripped them bare. The fact that those disks still exist means they were born right here. And they are huge. Tens of times bigger than our sun. That means they were born fast and hard. These giants live fast and die young. They scream through their fuel in a few million years. Compare that to our sun, which takes a leisurely 10 billion years to burn out. Seeing these massive youngsters near the black hole tells us star formation is happening right now, even in the middle of all this chaos. How is that even possible? Nobody knows. The big theory is that the gas somehow flattened into a dense, rotating disk, something strong enough to act as a shield against the black hole. Inside that protective shield, the gas could finally cool off and break apart, giving stars a chance to grow. The disk would be thick enough to swallow the radiation from the center, keeping the outer edges cool enough for stellar life to begin. In those cold, dark shadows, stars could finally form. But there is a catch. Our computer models show a disk like that should be totally unstable. The black hole gravity would kick up massive spiral waves in the disk, making the gas pile up into temporary, unstable ridges. Those waves might start the star-making process, but they also shove the gas around. Either it falls into the void or gets tossed out. The whole disk would either be swallowed or shredded within a few thousand years. That is nowhere near enough time for a star to actually form. Making a star takes at least a few 100,000 years. The cloud has to fall, break up, and then shrink even more before fusion ignites. It is a slow grind because that gas has to bleed off its energy. If it cannot cool down, it simply won't collapse into a star. Bleeding heat takes time. For a disk to last long enough to build a star near Sagittarius, a star, it would need to be incredibly stable. Maybe there is some mechanism out here holding that disk together. Something we have not even thought to put into our computer models yet. It could be magnetic fields. They might be weaving through the disk, giving it just enough backbone to resist falling into the dark. Or maybe the disk is constantly fed new gas, keeping its shape even as some falls and some escapes. But out here, I just don't know. The observations tell me that stars are forming, but my theory can't yet explain how. And yet, there they are. They're real. My physics says they shouldn't exist, but my eyes say they do. That is the Webb paradox. It is a pocket of cosmic life in an environment that should be a sterile graveyard. It gets weirder. Webb found more than just a few stars near the abyss. I see a whole hidden population of them. Hundreds, maybe more, once I've finished sifting through all the data. Before, ground telescopes and even Hubble only let me see the giants, the massive ones that screamed for attention. The center is so choked with dust and stars that only the most brilliant beacons could cut through. The rest were ghosts in the glare. But Webb's infrared eyes revealed a sea of cooler stars I never knew existed. Infrared light cuts right through that dust. It lets me see cold objects that don't glow in visible light. Red dwarf stars are a perfect example. They're small, chilly stars that mostly shine in the infrared spectrum. They're everywhere, maybe 70% of the galaxy, but they're so faint, I'd never see them without help. My instruments are sensitive to these cold stars, finding them all around Sagittarius A. Some are dying red giants. Red giants happen when a star like our Sun runs out of fuel. The core shrinks while the outside bloats. Their huge, cool surfaces glow in infrared. Others are main sequence stars, similar to our Sun but much older. These stars are just quietly fusing hydrogen in their cores, stable and totally normal, except for the fact that they're trapped in the most extreme environment in the galaxy. And many are where they shouldn't be. They're orbiting the abyss in wild, messy paths that ignore the galaxy's rotation. Usually, stars follow the rules. They orbit the center in neat circles, like cars moving together on a highway. This order comes from our birth. Billions of years ago, the Milky Way began as one big, spinning cloud. As that cloud collapsed, it flattened out. Every star born inside it just inherited that same smooth rotation. But the stars I see near Sagittarius A break the rules. Their orbits are tilted and stretched into chaotic ellipses. They're moving in every direction. It's like they've been kicked around by other stars or by the black hole. When two stars brush past each other, they trade energy. Gravity tugs at them both in a dangerous dance. One star might get flung into the void, while the other is pulled even closer to the black hole. These close calls are rare elsewhere. But here, where the star density is millions of times higher, they're common. Encounters happen all the time. Over eons, these hits have turned the orbits into the chaotic mess Webb revealed. It's a violent, terrifying place, and these stars are the survivors. They've been playing cosmic pinball for millions of years. They bounce off each other's gravity, and they're still here. But I know some stars aren't so lucky. Every once in a while, a star drifts too close to Sagittarius A and gets shredded by the hole's gravity. It gets stretched into a long ribbon of gas that spirals down into the mouth of the black hole. The beast feeds. For a short time, it flares bright as it devours the remains of that dead star. We call them tidal disruptions. They're rare, maybe once every few thousand years for a monster like this one. When they happen, they're spectacular, releasing massive energy. Now, let's look at the gas together. Webb caught these thick clumps in the gas, dense knots spiraling straight toward the edge of the void. I expected this. Gas falling into the abyss doesn't drop straight in. It spins into a disk first. Inside that disk, things get messy. Turbulence creates these dense pockets that shouldn't be there, but are. Gas orbiting close to the hole moves much faster than the gas spinning further out in the disk. This difference in speed creates a massive shear, which generates violent storms and whirlpools of gas. These are regions where gas piles up for a time before being tossed away again. Some of these density swings can grow, pulling in more gas and becoming even thicker clumps. But what I didn't expect was how organized these clumps are. They're not random. They seem to be forming a spiral pattern like the arms of a whole galaxy, but on a much smaller, more intimate scale. I think these spirals are density waves, ripples in the disk that move outward from the black hole. The black hole's gravity creates these waves, or maybe a massive object hidden deep inside the disk itself. As the wave moves through, it squeezes the gas. It creates these bright, high-density arms that I'm seeing now. Gravity is driving this spiral, but the details of how it stays so stable are still a mystery to me. In theory, these spiral density waves should be short-lived, forming and then fading as the gas flows. But this structure Webb observed stays stable, implying that something is continuously driving its motion. From my vantage point, maybe you and I are seeing a massive object embedded in the disk, creating a gravitational wake. Or maybe magnetic fields are stabilizing that spiral. I just do not know. And those clumps? They are screaming fast. They orbit the void at fractions of light speed. At the inner edge, gas moves at 30% of light. That is 55,000 meters per second. Up here, relativity is real. Time, dilation, and length contraction happen. Even mass increases as things accelerate. The gas down there feels a gravitational field so strong and fast. Einstein is essential to understanding what I see. As they spiral in, they heat up and emit radiation. Friction and compression cook that gas to millions of degrees. It bleeds X-rays and ultraviolet light into space. This light carries energy away, letting more gas drop. Without that cooling, the heat would halt the fall. Pressure would push back against gravity, stopping the spiral. But radiation provides the cooling we need. It lets the gas dive into the abyss. This is the fuel. When Sagittarius A feeds, it glows. When it gulps down gas, that disk outshines every star in our galaxy combined. I can barely imagine it. Some are so bright we see them from billions of light years away. Quasars, the brightest objects in existence. But looking out now, Sagittarius A is quiet. It is not eating, or at least, it is just snacking. It consumes almost none of the gas available. The clumps are there, spiraling, but not falling in yet. Most of it gets blown away by stellar winds or scattered by radiation before reaching the event horizon. The beast is surrounded by food, but it is starving. Why? It is a massive mystery in this void. They do not feed forever. They go through cycles, periods of intense hunting, followed by long, silent naps. During an active phase, the black hole devours gas clouds, growing and releasing enormous amounts of raw energy. The disk becomes a blinding spotlight, and powerful jets can shoot outward from the poles into deep space. Those jets stretch for thousands of light years. Magnetic fields in the disk twist and pull as gas falls. They tangle and twist until the magnetic field finally snaps, firing enormous jets of energy and matter out at nearly the speed of light. It is terrifying. Those blasts can wreck a galaxy, heating up gas and preventing new stars from ever being born. During a dormant phase like now, the black hole barely feeds, the disk is faint and jets stop. Its influence out here is minimal. You and I might wonder what triggers the switch. Nobody knows for sure. Maybe the food supply fluctuates. A star might get ripped apart, providing a temporary feast for the monster. Or a gas cloud wanders too close. When gas is plenty, it feeds. When it is dry, it sleeps. Or maybe the black hole regulates its own feeding. Its own activity might be what stops the meal. When it is active, those jets and winds blast the remaining gas away from the dinner table. It is called feedback. The heat keeps the rest of the gas from cooling down and falling in. This shuts off the fuel line, causing a dormant phase. Then, over time, gas piles up again. Eventually, it hits a threshold and falls. This cycle explains why these supermassive giants pulse like hearts. But the timing is a mystery. We do not know how long these naps last, or the active phases. I have seen evidence of past activity. By studying distant clouds, we found they are still glowing today. They glow in a way that proves they were hit by a burst of intense radiation quite recently. Those atoms were stripped of electrons. The only likely source is radiation from Sagittarius A itself. Here is the weird part. Those clouds are several light years away from the center. If it flared up, it would take years for that light to reach those banks, traveling through space. Based on that glow, our black hole had a massive outburst 300 to 400 years ago. Back in the 1600s, our central black hole was screaming with light and actively feeding. It was pumping out intense X-rays and ultraviolet fire. Then it stopped. Now, it sits there, silent. That light has faded, but the ionized clouds are still echoing the past violence of our galaxy heart. What caused that feast? Why did it end? When will the monster wake up and feed again? These questions remain, but the evidence is clear. Sagittarius A is not some static, dead object. It is dynamic, cycling between life and death every few centuries. That affects the entire galaxy around me. When it wakes, its radiation can stop star formation and create hot gas bubbles that last for millions of years. When it's quiet out here, stars are born more easily. These black hole cycles might actually control our galaxy's life, deciding where stars ignite and carving the very heart of this cosmic center. It is a massive shift. We used to view black holes as lazy traps, just floating in the void and swallowing anything that drifted too close. But now I see they are the true architects of the galaxy. They do not just react to their surroundings, they actively build them. Now, let us look at the absolute shocker water. The Webb telescope found it drifting around Sagittarius A out here that feels totally impossible. Water is such a delicate thing, just 2 hydrogen atoms and 1 oxygen hooked together in that familiar bent shape. Those atomic bonds are fragile, held by electromagnetic forces between positive nuclei and shared negative electrons. It is a weak grip for such a harsh place. Back home on Earth, water is tough and stable. Those bonds hold up perfectly under normal heat and radiation. But out here, in the nightmare environment of a black hole, water molecules should be wiped out instantly. The savage ultraviolet light and X-rays screaming from that accretion disk should shatter those bonds, reducing water to lonely, scattered atoms. 1 high-energy photon is all it takes to strike a molecule and snap those atomic connections like glass. It splits the water into hydrogen and oxygen atoms. We call that photodissociation, and it happens incredibly fast under such brutal ultraviolet light. Near Sagittarius A, that radiation should destroy water in under 1 second. Yet, through my sensors, the Webb telescope still sees it. It is not much, but it is definitely there, glowing in the infrared. Our instruments catch those unique signatures like a cosmic ID card. Every molecule absorbs light differently, leaving behind a specific pattern that works exactly like a human fingerprint. Water leaves a clear mark at 2.7 and 6.3 microns. It is an unmistakable signature drifting in the dark. We caught those signatures right near Sagittarius A, confirming water exists there. But how does it survive? The best guess is that it is forming constantly. Atoms of hydrogen and oxygen are constantly slamming together in that gas, forced into new bonds to create water. Radiation kills them off, but fresh ones rise to take their place. It is an endless, violent cycle of life and death. So, at any moment, some water survives. We call this chemical equilibrium, where the birth rate of molecules perfectly matches the destruction. The total amount of water stays steady over time, but this theory has major holes. That radiation should be winning this race by a mile. That means there should not be enough water for us to detect. To form, atoms have to collide with the perfect energy and exactly the right orientation to bond. It is an incredibly rare event in this thin gas, where atoms are spread far apart and flying around at such extreme high speeds. Once that molecule finally forms, the surrounding radiation should blast it apart almost instantly. The fact that we see water suggests the radiation is not as bad as we thought, or there is some hidden mechanism shielding the water from the fire. Perhaps water hides in dense gas clumps, tucked away where the surrounding radiation cannot reach the delicate molecules. Thick gas can soak up that energy, protecting the molecules buried deep inside. If these clouds are big enough, the water inside might survive for a while. Or maybe our math for this whole radiation environment is just wrong. Maybe that disk is not screaming with ultraviolet light like we thought. Or maybe space dust is scattering the fire before it can reach the water. It is a massive puzzle. Seeing water in this hellscape proves that chemistry can actually survive in places we once thought were far too extreme. It shows me that even in this violent chaos near a black hole, complex molecules can find a way to exist, if only for a moment. This changes everything for astrobiology. If water survives near a supermassive black hole, it makes me wonder what else is out there. Could organic molecules, the very seeds of life, form in this environment? We are talking carbon-based compounds like methane, formaldehyde, and the amino acids that build us. These are essential for life, building our cells and DNA. Back home, life makes them, but in the deep reaches of space, they can form without any biology at all. We have spotted organics in gas clouds, planetary atmospheres, and even riding on the backs of cold comets and asteroids. Could they form near a black hole? Probably not. The radiation out here is just too savage. Organics are even more fragile than water and would be destroyed much faster. But the fact that I am even asking proves how much these discoveries have changed our perspective. We are redefining what is possible. Just a few years ago, the idea of finding any chemistry near a black hole would have been laughed at. Now we see water and wonder what else is hiding, but then there is the mystery of that glowing, ionized gas. We spotted massive gas clouds around Sagittarius A, glowing fiercely in the infrared. That light tells me the gas is ionized, meaning its atoms have been stripped of their electrons. When an atom loses its electrons, it transforms into an ion, a highly charged particle. This ionized gas is strange. It conducts electricity and dances to magnetic fields, screaming out radiation at very specific wavelengths as its energy levels shift. By reading the spectrum of that glow, we can figure out the temperature, density, and even its chemistry. Ionization needs raw power. Something out there has to slam into the gas hard enough to knock those electrons loose. Out here, energy usually floods in from radiation nearby stars or the black hole itself. High-energy photons like X-rays or ultraviolet light are enough to ionize the surrounding gas. It works by dumping energy into atoms. When a photon strikes, it knocks an electron loose, ionizing the atom. But looking out at this specific patch, I see no obvious energy source. These gas clouds the Webb spotted are miles from any bright stars, and Sagittarius A is quiet, hardly emitting any radiation. The closest suns are light years away, far too distant to be lighting up these particular clouds of gas. Even the black hole's accretion disk is dim right now. It shouldn't have the strength to ionize gas at these massive distances from our vantage point. So where is the spark coming from? Maybe this gas was ionized centuries ago, during Sagittarius A's last big tantrum 300 or 400 years back, and it is still glowing. Ionized gas can actually hold that charge for ages if the density is thin enough out there. Usually, free electrons and ions eventually find each other again, neutralizing the charge through a process called recombination. But that takes time. In such thin gas, where particles rarely collide, it could take thousands or even millions of years to settle. If that last black hole outburst hit this gas, and it is thin enough, we might be seeing the remnants of that energy today. It would glow faintly as things slowly settle back to normal, but that does not quite explain everything we are seeing from the cockpit. Some of this glowing mist is in spots that should not have been touched by the black hole at all too far out, or just tucked away. Radiation bleeds out in every direction, but it fades. By the time it reached these clouds, it should have been way too weak to light them up like this. Maybe there is a hidden power source we have missed. Could there be hot, young stars buried deep inside those thick clouds of gas? They might be too dim or choked by dust for even the Webb to spot. Massive new stars blast out ultraviolet rays that can easily ionize space. If stars are hiding in there, they are the engine we are looking for. Or maybe we are seeing massive shocks rippling through the void. These happen when gas clouds slam together at high speeds, creating heat and ionizing atoms. Shocks occur wherever moving gas catches up to itself. The impact turns motion into raw heat, cooking the gas. If it gets hot enough out here, the atoms become ionized. Shocks happen when gas falls toward the abyss, when solar winds clash, or when a supernova blast wave shoves gas out into the dark. Any of these could ionize the gas near our central black hole, but none of them explain the full picture we are seeing. The way the gas is spread out, its heat, and its light signature do not match any single one of our theories. It is likely a mix of things, with different forces ionizing different pockets of the void in their own unique ways. This glowing gas is still a mystery, one that needs better data to solve. But wait, let us talk about intermediate mass black holes. This could be the biggest find in Webb's history. It might change everything I thought I knew about how these supermassive monsters actually grow. Floating among the stars and gas near Sagittarius A, The Webb found things that definitely do not look like normal suns. They are too small, too heavy, and they are tugging on nearby stars with terrifying gravity. Worst of all, these objects are completely dark. They do not shine, which is eerie for something that massive. Most stars glow by fusing hydrogen, turning mass into energy deep in their cores. Even the coldest, dimmest red dwarfs we see out here give off some kind of infrared glow. But these things are blacker than coal. They are also far too massive to be simple planets or even brown dwarfs. Brown dwarfs are basically failed stars, objects that tried to ignite but never got big enough to sustain fusion. They are usually 13 to 80 times Jupiter's mass, roughly 0.01 to 0.08 times the mass of our Sun. They are cold and dim, but we can still spot them in infrared thanks to the leftover heat from their birth. Whatever the Webb found is way heavier than a brown dwarf, and it is dragging nearby stars around with a massive gravitational grip. When a heavy object drifts past a star, its gravity gives a little tug, nudging the star off its path. We call that gravitational perturbation. It is one of our best tools for finding invisible monsters like black holes in the dark. By tracking stars near the galactic center, we can see tiny wobbles that should not be there. Those wobbles mean there is hidden mass nearby, something pulling on the stars while staying completely hidden from our eyes. Here is how we do it. First, we track a star's position over months or years, logging exactly where it sits in the void. Then, we calculate the orbit it should have based on the pull from Sagittarius A and the other visible suns nearby. If that star is moving exactly as we expected, the math and the reality line up perfectly. But if a ghost-like mass is lurking nearby, the star's position will shift. It gets pulled slightly off course by a hidden gravity well. By measuring those shifts precisely, we can spot the hidden object, guess its mass, and even figure out exactly where it is hiding. That is how Neptune was found back in 1846. We noticed Uranus was not following the path it was supposed to. Something was tugging on it, messing with its motion. By looking at the math, we figured out exactly where that hidden planet was, and when we pointed our telescopes at that spot, there it was, Neptune. Up here, I see the same physics at play near Sagittarius A, but those deviations are much smaller and harder to measure from this far out. Mostly, what I cannot see is just dark matter, or maybe ghost-like stars too pale for my instruments. Dark matter is the haunting substance making up 85% of the matter out here. It does not reflect or absorb any light, so it stays invisible to my eyes. I only know it is there because of its pull. From where I float, galaxies spin so fast they should fly apart without some hidden anchor. There has to be a secret weight out there tugging on everything, and we call that heavy ghost dark matter. Down in the galactic core, dark matter likely bunches up, maybe explaining the weird jitters Webb saw, or maybe just dim, tired stars. Not everything out here glows brightly. Those ancient, cold red dwarfs are nearly impossible for me to spot in the dark. If they are buried in dust, even Webb misses them. But sometimes, these movements are too massive for just dust or dim stars. Whatever is hiding out, there must be incredibly heavy and packed tight into the void. Webb's data points to monsters weighing hundreds or even thousands of suns, all squeezed into regions way too small to be normal stars. It is unsettling. Only black holes can pack that much punch into such a tiny space. They are definitely black holes, but not the small ones I am used to. These are intermediate beasts, thousands of times heavier than our Sun. From my perspective, it is absolutely staggering to think about. We have talked about these middleweights for decades, but detecting them from the silence of space has been nearly impossible. I know the common ones exist born when massive stars finally cave in on themselves. When a star weighing 20 times our Sun runs out of nuclear fuel, gravity just crushes the core. Once that collapse starts, I know nothing can stop it. That core shrinks down to a single point, opening a hole in the fabric of the universe. These common black holes weigh anywhere from 3 to maybe 100 times what our own Sun does. We find them by watching how they bully nearby stars or by listening to the ripples they make when they collide. Then there are the titans like Sagittarius A, millions of times heavier than the Sun. Most galaxies hide one right in the middle. I have seen them across the reach of space, from close neighbors to quasars billions of light years away. But how are they born? How does something weighing 100 suns grow into a monster 4 million times heavier than that? How do you get a billion-sun black hole less than a billion years after the Big Bang? It is the greatest unsolved mystery I see out here. The leading theory is that they just keep eating gas and swallowing other black holes until they are massive. You start with a small one, let it feed for billions of years, and hope it crashes into its neighbors. It sounds reasonable, but looking at the math, problems emerge. From what I see, black holes grow by pulling in gas from their surroundings. Gas does not just fall straight in, it spins, spiraling down into a glowing disk, like water circling a cosmic drain. As it swirls, the friction is so violent it heats the gas to millions of degrees. It is a terrifying furnace. That heat screams out X-rays and light so intense it actually pushes back against the very gas trying to fall in. That is radiation pressure. It is the same push that blows a comet's tail away from the sun. Even light has its own kick. When those photons slam into gas particles, they shove it away, literally pushing back against the abyss. For a hungry black hole, this pressure acts like a speed limit on how fast it can actually grow. Eat too fast, and the pressure gets so violent it blows your food away into the void, cutting off the supply. We call this limit the Eddington limit, after the man who first did the math nearly 100 years ago. For a black hole weighing as much as our sun, the limit is about 1/1,000,000th of its mass every year. For a 100-sun monster, it is 1/10,000th. It sounds like nothing, but over eons, it adds up. If a small hole eats at its limit for 1 billion years, it gets big. But here is the catch. Even feeding at the absolute maximum limit, it takes too long to grow from 100 suns to 1 billion. The universe is only 13.8 billion years old. The very first stars sparked to life about 13.5 billion years ago. They were not like the stars I see out my window now. They were born from pure hydrogen and helium. No carbon, no oxygen, no iron. Just the raw elements of the early void. Without those heavy elements, the gas could not cool down. Those early clouds just stayed hot and massive. Those stars were giants, hundreds of times heavier than our sun. When they died, they left behind massive black hole seeds. Imagine one of those giants leaving a black hole weighing 100 suns. That is the seed for a future titan. This new hole starts feeding at its absolute limit the very moment it is born. How long would it take to reach 1 billion suns? I can calculate that using growth. At the limit, a black hole's mass doubles every 50 million years. That is the Eddington time. Growing from 100 to 1 billion suns means expanding by 10 million times. It is insane. I am looking at 23 doubling times. That math equals 1.15 billion years of cosmic history. Looking out from my window, I realize that even feeding at the maximum rate, growth takes over 1 billion years to become 1 billion sun giant. Yet, we have spotted quasars feeding hungrily back at the dawn of time. From when the universe was only 600 million years old, those monsters already weigh billions of solar masses. There is just not enough time to grow that big by eating gas alone. Out here, the math simply fails. It gets more mysterious. Feeding is never constant. Sometimes there is a feast, and the hole devours everything rapidly. Other times, the void is empty, and the accretion process just slows down or stops. The active feeding cycle is likely way less than 100% of the time. If a black hole only eats 10% of the time, growth takes 10 times longer. The timeline breaks. Plus, not everything falls in. I can see powerful jets and winds blowing gas right back into the void. This slows the growth even more. It is getting harder to explain how these giants formed so incredibly fast. There must be another way. Maybe mid-sized black holes are the missing link, giving the giants a head start. That would let them reach supermassive status way faster than we thought. A 10,000 sun seed only needs to grow 100 times to become 1 million sun monster. Instead of growing 10,000 times over, it saves so much time. But how would they even form? They might form in crowded star clusters, where suns are packed tight enough to collide and merge. Ancient clusters were likely much denser. I imagine stars slamming together out here to create massive glowing giants. These massive suns would burn out fast, collapsing into mid-sized black holes in the dark. Or they could form directly from massive gas clouds, skipping the star phase entirely. Ancient gas clouds were far more massive than what I see today, lacking the heavy elements we have now. If a huge cloud collapsed, it could turn into a black hole instantly, bypassing any stars. We call these direct collapse holes. They start out weighing thousands of suns right from the beginning. But honestly, we have had very little proof they exist. A few hints here and there, but nothing solid. Some old star clusters seem to hide them at their cores, judging by how those stars orbit. We have even felt gravitational waves from mid-sized black holes merging out in the deep silence. But it is still debated. Are these real mid-sized holes, or just the largest of the small ones? The observations from the Webb telescope are about to change everything. If what Webb found near our galaxy's heart are mid-sized holes, it confirms they are real. Come with me as we watch them interact, merge, and feed on the surrounding gas. This would change everything. It shows that black holes do not just grow by slowly sipping on gas clouds. They grow by devouring other black holes, including these mid-sized ones. Our own Sagittarius A star probably reached its mass of 4 million suns by swallowing hundreds of these holes. Over eons, each merger sent ripples through space-time. Detecting those waves would prove this whole story. But those old waves have already passed us by. We cannot observe them directly anymore. We can only guess based on the size of our galaxy's center. If they are there, they are everywhere. This might be the primary way all massive black holes in the universe actually grow. Every giant might be surrounded by a swarm of smaller holes that it slowly consumes over billions of years. That explains how these giants grew so incredibly fast at the beginning of time. They start big, maybe from direct collapse, then grow rapidly by merging and feasting on gas. We need more data. Webb gave us a glimpse, but we need follow-up studies to be certain. Soon, we will track their orbits through the void with total precision. By watching them dance with nearby stars, I can help calculate their true mass and power. If the mass and orbits match, it confirms the mystery we have been trying to solve. We will also hunt for more gravitational waves from these mid-sized mergers. You and I will see new tools like LISA catch those low-frequency whispers from the deep dark. These low-frequency waves come from mergers of intermediate and supermassive black holes deep in the void. If LISA detects those ripples from the galactic center, I will finally have direct proof of those hidden giants. I will be watching as we refine our models using new data from Webb and other eyes in space. By matching what I observe with our simulations, we can finally determine how these supermassive voids actually grow. Let us look at this together from up here. Every discovery Webb makes around Sagittarius A ruins our old theories. Stars blooming in forbidden zones, water molecules surviving the impossible, ionized gas burning with no clear source of power, medium black holes hiding in plain sight, a dormant giant surrounded by fuel, cycling between states over several centuries. Any one of these would be huge. Together, they completely flip my understanding of how the cosmos works. This applies to the most violent corners of the universe. These black holes are not just strange cosmic objects. They do not just sit in the center of a galaxy doing nothing. They are active players in evolution. When a supermassive hole feeds, it releases blinding energy. This heat scorches the surrounding gas, stopping it from cooling. That heat stops new stars from forming. In a way, one active black hole can murder a galaxy future. We call it AGN feedback, active galactic nucleus feedback, and it is what keeps our entire universe in check. Without that feedback, galaxies would burn through their gas too quickly, leaving nothing for any future generations of stars. Our models without this feedback produce galaxies that are too massive and way too blue, meaning too many stars. Those simulations do not look like the real galaxies I see out here, but add feedback, and observations match. The feedback chokes off star formation and scatters heavy elements into the deep, dark abyss between the stars. By blasting gas into the abyss, this feedback stretches out the life of a galaxy over much longer timelines. This lets galaxies keep birthing stars for tens of billions of years, creating the beautiful views we see today. These are the galaxies with a mix of old and young stars, where life slows down gradually across time. The problem? I still do not fully understand how this feedback works, or what actually wakes these monsters up. I do not know what determines that energy blast, or how it really grabs hold of the galactic gas. Is the feedback efficient? Is it the same everywhere? Or does it change depending on the galaxy's own properties? These are the big questions, because this feedback is now baked into every major simulation of galaxy formation. Without it, our maps of the cosmos fail. They give us galaxies that are far too heavy and vibrant. Those models show stars forming at a breakneck pace. But the feedback is just a simple mathematical guess. It is just a basic formula trying to explain a terrifyingly complex physical process that we do not quite grasp. If our understanding of the physics is off, our simulations might be producing right results for the wrong reasons. That means our predictions for the future of our home are shaky, but Webb is giving me some clues. Sagittarius A is sleeping despite being surrounded by fuel. That tells me something is strictly controlling when it eats. It is not just about gas availability. I see gas spiraling around that void, but it is not falling in. Something is holding it back. Maybe it is the rotation of the gas, creating a force that fights against infall. Or maybe magnetic fields in the disk are pushing some gas out while letting just a tiny bit slip. Perhaps even while dormant, the black hole produces winds or jets that scream through the silence and blow gas. I do not know. But evidence from 300 to 400 years ago shows these transitions can happen incredibly fast. These changes happen on human timescales. That is huge. It means we might actually witness one of these transitions. If Sagittarius A wakes up in the next few decades, I will have a front row seat to watch it. We will track the rising light, the shifting gas, and see exactly how our home galaxy responds to the beast. That would be priceless data. Seeing young stars near the center tells me that new life can find a way. Even with an active black hole nearby, stars can still form. This cosmic feedback is not a total shutdown. It does not kill everything at once. It is more subtle, hitting different areas differently, depending on local conditions. In some spots, the feedback is a death sentence for stars. In others, dense gas acts like a shield. Starbirth continues despite the chaos. This is key. Feedback is not just a simple light switch you flip. It is a spectrum, a range of power that shifts across the void. The exact strength depends on many factors. All these factors decide the fate of a galaxy. These views force me to rethink reality and its complexity. From my vantage point, the black hole rules star birth through its feedback. Yet, the stars strike back, fueling the monster with the gas it needs to grow. It is a perfect, two-way loop, a cosmic dance of life and death out here in the dark. Cracking this cycle is key to knowing how galaxies grow. Out here, I wonder, is this happening in every corner of the void? Is Sagittarius A freak of nature or just a typical giant? We only have this one example to look at from our cockpit window. If it is unique, then Webb's data might be useless for understanding the rest of the dark universe. The results could just be quirks of our own galaxy. Maybe its mass or some strange local trait makes it an outlier in the deep dark. But if what I see here is common, if all supermassive hearts share this environment, then these findings change everything we know about the entire universe. They reveal a fundamental truth about how these monsters function not just in our backyard, but in every distant galaxy. We are still guessing. It is just that this one is our closest neighbor, letting us stare into its abyss from relatively close range. From 26,000 light-years away, Webb can pinpoint individual stars and gas clouds at the center, measuring their speed and position with the most incredible precision. The other giants are lost in the distance, making them nearly impossible for us to study. Andromeda, our closest big neighbor, is 2.5 million light-years out. That is 100 times farther than our local monster. At that range, even Webb cannot pick out single stars near the core. We just see the galaxy as a blurry, glowing whole. We can gauge the center's total glow, but we cannot isolate single objects like we do at home. Beyond our neighborhood, the sheer vastness of space becomes incredibly daunting. One example is not enough. To truly understand these gravity wells, we need to peer into many more of them from out here. We need a massive data set, watching black holes of every size and age across all kinds of strange, distant galaxies. Only then can we see what is normal and what is a freak occurrence. We have to separate universal laws from unique accidents. Webb is finally beginning that hunt, scanning the hearts of other systems for these same mysterious patterns. It is a brutal task because most targets are so much farther away than ours, yet Webb's power makes the impossible possible. It can find faint objects across billions of miles, its infrared eyes cutting through thick galactic dust just like it does in our own. The work is ongoing, and we will be crunching data for years, but what I am seeing in these early reports is promising. Early data from our closest neighbors suggests that the strange things we saw at our own galaxy's core are not unique at all. It appears our black hole is far from being alone. Other cores show stars being born in hellish conditions, strange glowing gases, and the potential for medium-sized black holes hiding in the dark. Take NGC 1068. It holds a supermassive giant with a mass of about 15 million suns, right at its heart. Webb spotted baby stars being born just a few light years from that monster. Exactly like what we saw happening right here in our own backyard. Then there is M87. Its black hole is a true beast at 6.5 billion solar masses, screaming with a jet that blasts thousands of light years into the void. We are still watching M87's core, but the early images show a chaotic mess of gas and perhaps even more hidden, medium-sized black holes. This suggests these events are common, perhaps even universal across the void. Every supermassive void out there might be a chaotic storm where stars live and die, and where gas is sucked in or spit back out, where smaller black holes hide, waiting to be devoured by the central monster. If that is true, we have to rethink everything we know. Galactic centers are not quiet or passive places. They are violent, evolving systems that essentially dictate the fate of the entire galaxy. The black hole at the heart of it all is not just sitting idle. It is regulating the birth of stars, blasting the gas with heavy elements from its jets, and growing bigger by devouring everything in its path. Every one of these actions shapes how the galaxy evolves. You and I should look at how we actually caught this. Understanding Webb's methods makes you realize just how impossible this mission felt. Infrared astronomy is brutal. It is all about heat. Anything warm glows in infrared, including the very telescope we are using to look. If the machine gets warm, its own heat will drown out the tiny, flickering signals coming from the edge of the universe. To fix this, Webb has to stay incredibly cold. It operates at negative 390 degrees Fahrenheit, which is just 50 degrees above absolute zero. Absolute zero is the end of the line, the temperature where even atoms stop moving entirely. That is negative 459.67 degrees Fahrenheit. At only 50 degrees above that, Webb is colder than any natural environment found in our entire solar system. It is colder than Pluto, colder than the void between stars, colder than almost anything besides the very echoes of the Big Bang. This extreme cooling comes from a massive sunshield the size of a tennis court. It is built from 5 layers of kapton, a reflective film that is incredibly good at blocking out heat. Each layer is separated by a small gap, forming a perfect insulating wall against the sun. That shield kills the heat from the sun, Earth, and Moon, letting the telescope fall into a deep, dark freeze. On the side facing the sun, it is a blistering 185 degrees Fahrenheit, enough to boil water. But on the dark side, where the telescope hides, the temperature drops to negative 390. That 500-degree difference is all thanks to the genius of that sunshield's design. At these freezing temperatures, Webb kills its own heat, letting me catch faint infrared signals from deep space. But even with this chill, peering at Sagittarius A star pushed us to the edge. The galactic heart is blinding. Millions of stars are out there, bleeding infrared light. Together, they create a wall of impossible, glowing glare. This light drowns everything out. It is like me trying to spot one candle flame in a brightly lit stadium. To see through this glare, you and I need the most sensitive eyes ever built. That is NIRCam. NIRCam is the sharpest camera we have ever constructed. It counts every single photon, building an image piece by piece. It catches light from 0.6 to 5 microns. That is the near-infrared range we are hunting in. That is right on the edge of what we can see. At 0.6 microns, it just touches visible red. It bridges the gap between sight and heat. At 5 microns, I am seeing the literal warmth of distant, dark objects. Its resolution is 0.1 arcseconds, deadly sharp. An arcsecond is just 1/3600th of a degree. Think of it this way. The full moon we see from Earth is 1800 arcseconds across. This is tiny. 0.1 arcseconds is like spotting a penny from miles away. And Sagittarius A star is 26,000 light-years off. This lets me see objects just 0.02 light-years apart. That is roughly 1240 astronomical units. 1 astronomical unit is the distance from our Sun to Earth, about 93 million miles of empty space. So, we can distinguish points 115 billion miles apart, way over at the center of our galaxy. That sounds like a massive gap, but the space around Sagittarius A star is packed tight with millions of stars. Stars there are jammed together, usually just a few light-years apart, but sometimes as close as a few hundredths of a light-year. Picking out one star from that crowded abyss took incredible precision and a very careful plan from our team. We watched in different infrared colors. This helps us tell one object from another based on how they glow. Hot, young stars shine bright at shorter wavelengths. They pour out energy in the near-infrared, around 1 to 2 microns. Older, cooler stars glow at longer wavelengths. Red giants and dwarfs bleed their light in the mid-infrared, near 3 to 5 microns. Even the gas and dust have their own signatures, glowing at specific points, depending on what they are made of. Hot gas screams in a constant infrared stream. Cooler dust vibrates at specific notes, revealing the molecules hidden inside the grains. By layering these wavelengths, we map the temperatures of stars and the swirling distribution of gas and ancient dust. We call this multi-wavelength imaging. Stick with me, because processing this data was a real challenge. Webb's raw images were a mess. Millions of stars all bleeding into a single chaotic jumble of light. Every star should be a point, but they are so crowded, their light overlaps, creating a nightmare of tangled patterns. I needed complex algorithms to untangle them, to measure their brightness and track how they move through the void. This is photometry. We fit math models to the light to pinpoint exactly where each star is and how it burns. We compared my new data to old shots from other telescopes. We were looking for anything that shifted or flickered. Stars near Sagittarius, A star, are flying. They orbit that black hole in anywhere from a few years to millennia. By checking images over time, I can actually watch them move. I am literally tracking their orbits around the dark. This maps out the black hole's gravity. Then, we used spectroscopy to find the invisible, ionized gas clouds. Our spectrograph, NearSpec, splits infrared light into its parts. It creates a rainbow that tells a very deep story. A spectrum is like a barcode from the stars. It shows me exactly which wavelengths are there and how bright. Every atom leaves a fingerprint. That unique signature tells me exactly what that gas is made of from light years away. Take hydrogen. It glows at specific points as energy levels shift inside the atom. It is a cosmic beacon. When an electron drops to a lower level, it spits out a photon. That photon has a very specific, telltale wavelength. These marks are the ID for hydrogen. They let me find it floating in the clouds right around Sagittarius A star. We could tell the gas was ionized. We measured the heat, the density, and even found traces of water molecules out there. Even the shape of those lines tells a story. If gas is moving, the lines shift, sliding toward the red or blue. If it is hot, the lines blur. Those atoms are moving so fast, they create a wide range of Doppler shifts. All this info is hidden in the spectrum. We also used it to find intermediate mass black holes lurking nearby. We see them by how they pull on stars. If an orbit is warped by something invisible and massive, it is likely a black hole. By tracking those star paths and finding anomalies, we can prove these hidden giants exist and even calculate how heavy they are. We use dynamical modeling, a way to spot those invisible black holes lurking out there in the deep dark. That is how we found Sagittarius A. I build these mathematical models to predict exactly how gravity should pull nearby stars toward the great abyss. Then I compare the math to what I see. If the star's path doesn't match our model, it means some hidden mass is out there. By tweaking the math, we can find exactly where that ghost is hiding in the dark. It takes months of staring into the void and years of checking the data. Tonight, I am sharing work from hundreds of colleagues on Earth, all trying to decode what Webb sees from up here. My team analyzed data, ran simulations, and checked each other's theories over and over again. This is how we explore today. We cross borders to push the limits of what humans can know. And believe me, this is just the start. The Webb telescope keeps its eye on Sagittarius A, and we learn something new with every pass. Over the next few years, I will be watching as Webb maps the galactic center, building a clear picture of the environment around that black hole. Now, let's talk about the future. What happens next? What wakes that sleeping giant back up? You and I don't know yet, but there are clues. Usually, these phases start when a massive pile of gas and debris suddenly falls straight into the void from the surrounding space. If a star drifts too close, the gravity will rip it apart. We call that a tidal disruption. The shattered star forms a glowing ring, and the black hole feeds on it for months. It creates a flare so bright it is haunting. These events are rare, but once a star enters the kill zone, things get violent. The gravity pulls harder on one side of the star than the other. It stretches the star into a long, glowing ribbon before tearing it to shreds. The remaining debris wraps around the abyss like a ghost of what once was. When that gas hits the event horizon, it glows with an intense, deadly heat. The resulting flare can outshine our entire galaxy for months. My charts say a tidal disruption like this happens maybe once every few thousand years. It all depends on how crowded things are down there and how those stars are moving. In this crowded space where millions of stars orbit within a few light years, seeing a star get torn apart is actually quite common. The last explosion might have happened 300 to 400 years ago. But up here, nothing is certain. The evidence just suggests something big went down. Maybe it was a star dying, or perhaps just a massive cloud of gas getting swallowed. The next one could happen in 1,000 years, or tomorrow. Up here, we have no way to predict it. Those orbits are pure chaos. Knowing when a star will drift into the mouth of the beast is impossible. We know the odds, but not the timing. A stray gas cloud could be the trigger. I see several massive clouds drifting nearby. Every so often, the black hole's pull catches one. In 2014, a cloud called G2 drifted too close. We thought it was game over for it. We aimed our scopes and held our breath, waiting for the fireworks. But nothing happened. It survived, slipping past the abyss untouched. It just proves that we still do not fully understand how gas moves around these cosmic monsters. Why did it live? I have a few theories. Maybe the cloud was denser than I expected, holding together against the gravity. Or maybe it had a star at its core, keeping it bound. Or maybe our math was off, and it did not pass as close to the danger zone as we feared. There are others out there. Webb is watching those clouds closely, waiting for the next near miss. If one falls, we will see it. But there is also the chance of a much more gradual build-up of material in the dark. A constant stream of gas is trickling into the center as we speak. Stellar winds and the ghosts of dying red giants are all being sucked slowly toward the middle of the galaxy from the void. Most of that gas never reaches the mouth. It gets scattered or burned away by radiation before it ever hits the point of no return. This trickle feeds the accretion disk, but the rate is too low to wake the beast. Right now, it is just sleeping peacefully. Over time, that gas can pile up in the disk. If enough of it builds up, the whole thing becomes unstable and falls in. We call this a thermal instability. It is like a cosmic fuse that triggers a massive outburst. At low densities, the disk stays calm and stable. But if it gets too thick, it can suddenly ignite into a hot and very unstable state. The gas will plunge inward. That black hole will ignite and become the brightest thing in the sky. So, we wait. You and I are watching the monitors for any sign that the monster is finally waking up. I see the brightness shift the light around that abyss is changing, and the gas is swirling in strange ways. These are warning signs. Something's coming. When that black hole wakes up, we'll have a front row seat to the chaos. We'll watch the darkness ignite in real time, seeing massive jets blast outward as the surrounding gas begins to scream and burn. From here, we'll see the disk flare up. X-rays will surge while those terrifying jets stretch further into the deep silence. It's our chance to see how this monster feeds and how it reshapes everything in its path. We'll finally test our theories against the raw reality out here. Meanwhile, the Webb is still spotting things that shouldn't exist. Every time I look out the viewport, I see something that defies logic. It's unsettling. Things are moving so fast. Every few months brings a new mystery that leaves us staring into the dark, searching for answers. We've entered a golden age. My eyes and our senses can finally see the things we only dared to imagine decades ago. For decades, we had nothing but theories, lacking the eyes to actually look into the mouth of the beast. Now, with the Webb and our newest tech, we're finally seeing these gravity wells in the terrifying detail they deserve. Reality is much stranger than my training suggested. It's a paradox life and creation happening in a place that should be dead. This strange persistence of life is the thread connecting everything I see through the Webb's lens. Radiation should kill everything here. Gravity should rip atoms apart. Yet, I'm watching brand new stars flicker to life in the chaos. Water is out there, and complex chemistry is happening. It's like nature refuses to follow our rules. My manuals say star formation here is impossible, but the universe finds a way. That water should have evaporated instantly, yet I see it glowing in the Webb's infrared haze. The gas is glowing without an obvious source. It seems wherever there's a tiny chance for structure, nature fights to exist. It's a profound realization. These extreme corners of space aren't just empty graveyards or dead zones. They aren't sterile or empty. They're alive, shifting, and constantly throwing surprises at us from the shadows. These are the places where physics breaks, where the rules are pushed so far that something entirely new begins to happen. The cosmos is far more creative than we thought. It refuses to stay simple or boring. It builds order right out of the heart of chaos. And the implications of that reach far beyond these black holes. If stars can be born near Sagittarius A, where else are they hiding? What other dead zones are actually nurseries? Maybe they're forming around neutron stars, spinning wildly with magnetic fields that should crush anything nearby. Or maybe inside those massive jets screaming at nearly the speed of light, or within the debris left behind after a star just exploded. These places are hostile and terrifying. But if I've learned anything out here, it's that our sense of impossible is usually wrong. Space is full of secrets. If water survives next to a black hole, what else is lingering in the dark? Is complex organic chemistry happening out there? Those are the very building blocks of life, floating in the void. We're talking about methane, sugars, and amino acids, all drifting through the most violent regions of the galaxy. On Earth, life makes these, but out here in the vacuum, they're forming without any help from us. We found them in clouds, on planets, and inside drifting asteroids. They are everywhere in the silent medium between stars. Could they survive near a black hole? Is life's foundation being laid in the one place we never dared to look? It sounds crazy. But then again, so did finding water in a gravity well just a few years ago. It all sounds like science fiction, but remember, so did the idea of stars being born inside a black hole's shadow. The Webb has shown me that our maps are incomplete. There's so much we don't know yet, and it's exhilarating. This is why I'm out here. Not to prove I'm right, but to be surprised by the things I never expected to find. Every time we peer into the deep dark and see something strange, we get closer to the truth of how this universe works. We're rewriting the manuals as we go. What I'm seeing at Sagittarius A is the perfect example of that. I thought I knew what to expect, a sleeping giant surrounded by ancient, dying stars and a little bit of dust. The center of the galaxy should be a quiet place, just a passive hole in space, occasionally consuming gas, while mostly doing nothing else. Instead, I'm seeing young stars, water, and even more black holes lurking. Everything I was taught is being challenged. Every prediction was wrong. The center isn't quiet, it's a chaotic hive of birth, death, and swirling gas. Now we're scrambling to understand it. We have to build new explanations for the impossible things I'm witnessing. The team back home is running the numbers again, trying to figure out how the physics I see can actually exist. We're already planning our next look, hunting for more evidence. This is how we move forward, one mystery at a time. Progress doesn't move smoothly up here. It arrives in sudden, jarring leaps. When new data forces me to rethink everything, it is messy, chaotic, and completely thrilling. I want to leave you with one final thought as I look out at the void. Sagittarius A is 26,000 light-years away. When I gaze at it, I am not seeing it as it exists now. I am seeing it as it was 26,000 years ago, long before any human city ever touched the Earth. The light this telescope captures left that black hole during the last ice age, back when woolly mammoths still walked the frozen ground. In that era, my ancestors were barely starting to farm or settle down. They lived as hunters and gatherers in tiny wandering groups. They trailed animal herds for food. They had fire and stone tools, but they had not yet imagined writing or the cities I left behind. Yet, in that same ancient moment, light was already fleeing Sagittarius A. It carried secrets about the black hole environment through the dark. That light drifted through the void for 26,000 years. It crossed the galaxy, piercing through thick clouds of gas and cosmic dust. Finally, in 2023, it struck the mirror of the Webb. My instruments captured it right here in the silence of space. Everything I see, the baby stars, the water molecules, the glowing gas, all of it happened 26,000 years in the past. Right now, those stars have likely aged. Some might have already died in violent supernova explosions, scattering their remains across the galaxy. Those water molecules were probably destroyed and reborn 1,000 times. The gas has likely spiraled deeper toward the event horizon, or maybe stellar winds blew it away. Even Sagittarius A might be different now. Perhaps it is currently in the middle of a violent, active phase. I will not see that for another 26,000 years. Or perhaps it is still sleeping, unchanged from what I am observing. I simply cannot know. That is the haunting reality of space. I am always looking into the past, watching light that traveled for billions of years. I can never see the universe as it is right now, only as it was. For galaxies billions of light years away, I see them as ghosts. From billions of years ago, when everything was younger. Some of those galaxies might be gone now, destroyed in collisions or unrecognizable. Yet, this doesn't make my work less valuable. The laws of physics are the same out here as they are everywhere. What happened around Sagittarius, 26,000 years ago, shows me how black holes work, how stars ignite, and how galaxies evolve. These are universal truths. They apply not just to my home galaxy, but to every corner of the universe throughout cosmic history. The physics of starbirth is the same now as it was then. I watch gas clouds collapse under the crushing weight of gravity. When gravity beats the internal pressure, they shatter into smaller clumps while they fall inward. Those clumps just keep contracting, turning energy into raw heat. Eventually, the cores get hot enough for nuclear fusion to spark. That is how stars are born. This process is universal, ruled by thermodynamics and gravity. The tiny details might change depending on what the gas is made of. Temperatures or the environment might shift, but the core process stays. Black holes follow these same terrifying equations out here. Einstein's general relativity from a century ago describes how mass warps spacetime. That curve is what I feel as gravity. These equations apply to everything I see, from planets to black holes. They do not drift or change over time. A black hole born a billion years ago obeys the exact same rules as one forming right in front of me today. The event horizon is always at the Schwarzschild radius, set only by the mass. Out here, light always follows the geodesic path. Those are the straightest paths through curved spacetime. Time actually runs slower near massive objects. These are not just simple models. They are precise descriptions of how my reality works. Even the chemistry of water molecules follows these same ironclad rules. Hydrogen atoms have 1 proton and 1 electron. Oxygen atoms have 8 of each. It is consistent across the void. When 2 hydrogens bond with an oxygen, they form that familiar bent water molecule. Its properties are the same everywhere. This happens whether it occurs back on Earth, out here in interstellar space, or right near a supermassive black hole. Atomic bonds are ruled by quantum mechanics and electromagnetism. These are principles that simply do not change, no matter where I fly. By peering into the past, I am learning about my present and my future. I am discovering how this universe actually works. I am uncovering the laws that rule reality, regardless of time or place, and I am finding the universe is far stranger. It is more complex and beautiful than I ever imagined. It refuses to fit into the neat little boxes I build. Every time I think I understand a phenomenon, new data reveals hidden complexities. Every time I build a theory, nature shows me more. Nature shows me things that break my theories. This isn't a flaw in my method, it is a feature. It is how I progress. I build models from the data I have. I test them with new observations, and when they do not match, I refine them. Sometimes I just tweak a few parameters. Other times I have to throw out the old models and start completely from scratch. The history of physics is full of these revolutions. Newton's laws of motion worked beautifully for centuries before I got here. Then observations of Mercury's orbit and tests with the speed of light revealed tiny, alarming discrepancies that changed everything. Einstein developed relativity to explain those gaps. In doing so, he revolutionized how I understand space, time, and gravity itself. Quantum mechanics grew from observations that our old physics simply could not explain. Radiation patterns, light effects, and stable atoms, all of it pointed toward a fundamental shift in how nature actually works. Floating here, you and I are at a new frontier. We have 2 massive theories describing reality in totally different ways, but they do not mesh. Looking towards Sagittarius A, Webb sees things that push our best theories to their absolute limits. Every scan brings more mysteries and deeper puzzles. That is why being out here, doing this work, feels so rewarding. The James Webb Space Telescope has handed us a profound gift. It has proven we can peer into the most extreme places, the edge of a black hole 26,000 light-years away. Behind walls of dust, nature persists. Stars ignite where they should not. Water stays liquid where it should have been destroyed. Chemistry thrives in total hostility. And black holes, those cosmic monsters we thought we knew, are finally revealing their true faces. They are more mysterious than I ever imagined. Not just static drains in space, but living, breathing, and evolving entities. They live in complex webs of stars and gas. They sleep and wake, somehow regulating the evolution of the host galaxy around them. Feeding on gas and merging with other black holes, they create strange environments where our known laws of physics are pushed to their absolute limits. This is only the start. Webb will keep its gaze fixed on Sagittarius A for many years to come. Every new transmission will uncover details, solving old riddles while whispering brand new ones into the dark. I will watch stars form in real time and track gas as it spirals toward the void while searching for hidden black holes. We will wait for the next flare. With every find, we will rewrite the books, refine our models, and rethink everything. We are moving closer to the truth. The heart of our home galaxy is no longer a dark mystery shrouded in cosmic dust. For the first time, we see it clearly chaotic, violent, and beautiful. Thanks to Webb, the view is now finally crystal clear. What I am seeing forces us to reconsider everything black holes, how stars are born, and how galaxies actually grow. The universe has spoken. It told us our theories were half finished, and that reality is stranger than I ever dreamed. It has shown us that even the harshest places are living systems where new structures and strange phenomena constantly emerge. Now, my job is to listen and learn. Together, you and I are standing at the edge of a completely new level of understanding. The universe out my window is far more complex than we ever knew. Thank you for joining me on this journey into our galaxy. If you enjoyed this mission, a like or subscribe helps me keep sharing these deep space updates with all you curious minds out there. Remember, the next time you look up at the sky, know you are staring into a universe filled with many surprises and endless wonder. We are only just beginning to understand. The stars you see are part of home, but at the center, invisible to our human eyes, visible only through Webb's infrared lens, sits Sagittarius A, a massive black hole surrounded by impossible stars and gas. 26,000 light-years away, hidden behind thick walls of dust, a massive cosmic drama is finally coming into focus for us. Stars are being born in the most hostile places. Water molecules are somehow surviving against all impossible odds. Smaller black holes lurk in the shadows, while the giant at the center cycles between activity and rest, shaping our entire galaxy. The universe is stranger than we think, even stranger than we can imagine. That is why I love exploring it. Every scan brings the unexpected. Every discovery raises a question. Every answer leads me deeper into the mystery. This is the joy of science and the thrill of discovery. You and I live in an age where we can peer directly into the black holes. We can watch stars ignite in impossible places and find molecules in the most extreme corners of our space. My instruments see farther than ever, revealing a cosmos much stranger and more beautiful than anyone before us could have dreamed. Webb has many years of work left. Each year will bring new finds, new surprises, and fresh mysteries to solve. The universe is vast and ancient. I feel incredibly lucky to be living in a time where we can finally explore and marvel at it all. Good night. Sleep well down there, under the stars.